A gram of gold costs £45 currently, and a cubic centimetre of gold weighs about 20 grams. It's actually more like 19.3, but we'll go with 20 to make the maths easier. How much would a solid gold six-sided die cost? This particular one is a centimetre by a centimetre by a centimetre. So the way you use those two bits of information is to treat them as what they are. They're essentially a ratio between the three different things. We've got cost, mass, and volume. We have one connection between the cost and the mass, and another connection between the mass and the volume. And we don't care about the mass of the die. In fact, all we care about is the fact that we know it has a volume of 1 cubic centimetre. We want to cut the mass out of the equation, get rid of the middleman, and leave ourselves with the cost per cubic centimetre, the cost of a 1 by 1 by 1 centimetre gold die. And the way we do this is the way you would probably expect to. If you've got a single cubic centimetre, then it must weigh 20 grams, and for each of those grams the cost is £45. So we multiply them together. Now, having written it in this derivative form, hopefully you can see the dm bit cancels out. That's not exactly what's happening, but it's pretty much what's happening. These derivatives are infinitesimals. In a sense, they're so small that they're smaller than any number, and yet they're not quite zero. We've got a ratio between them. They're a limit, effectively, what very small changes are tending towards. But at the end of the day, it's nice to know that it works out like this. We can treat fractions involving derivatives, dy by dx, dx by dt, etc., etc. We can treat those in much the same way that we treat fractions when we multiply them. So the rate at which the cost changes per gram combines with the rate at which the mass in grams changes per unit volume to give us the overall rate at which the cost changes per cubic centimetre. You can get yourself this dice for £900. Or, as my son points out, you can save yourself a little bit of money because it's got dimples in. I think I worked out you could save yourself just under 40 quid. So there you go. This is a principle called the chain rule. It's an idea behind a lot of important differentiation techniques. It will widen the horizons of the kind of functions you can work with, and we're going to start with it just within the context of parametric equations because we're just finishing that topic. What the rule tells us is that if you know the rate at which y changes with respect to t, let's say, this third parameter, and you also know the rate at which x changes with respect to t, and that second one can get flipped over, and it's just 1 over dx by dt in case you're wondering, well, those two rates can be combined and we can use it to eliminate and cancel out the dt, leaving us with exactly what we're probably interested in, dy by dx, our old friend, the rate at which y changes with respect to x. Let's see what this looks like with an example. Here's a parametrically defined curve. I've mentioned this one in a previous video. X equals t squared minus t, y equals t squared plus t, and t can be any real number. So we can get a rough sense of what this is doing by thinking about what happens when t is very large negative and what happens when t is very large positive. And we can think about what happens when t is 0, for instance. T is 0 is a nice one to start with. Clearly this curve goes through the point 0, 0, because when t equals 0, x and y are both 0. But x and y are both positive quadratics, which means x starts high and ends high, and y starts high and ends high. So this is a quadratic which somehow the curve will start in the top right hand corner of the graph and it will end in the top right hand corner of the graph. What it does in between we're going to need to make sense of by trying a few more values. But let's begin by working out dx by dt and dy by dt. This is no more complicated than standard differentiation. The only difference is that the parameters we're dealing with look different. So we have an x and a t and we're finding dx by dt. We just differentiate everything on the right hand side with respect to t. So t squared becomes 2t and negative t becomes negative 1. Same sort of thing happens with dy by dt. We get some nice straightforward expressions. You'll notice they're both in terms of t. That kind of makes sense. dx by dt we were differentiating an expression involving t, and dy by dt we were differentiating y, which was an expression involving t. But we can find dy by dx from those, or we can look first at what those things themselves do. It's interesting to notice that dx by dt gives a value of 0 when t is a half, and dy by dt is 0 when t is minus a half. That means the rate at which the x coordinate changes is 0 at a particular point when t is a half. That's when it's no longer moving right and starts moving left, or no longer moving left and starts moving right. And for dy by dt, that's the moment at which it stops moving down and starts moving up, or maybe stops moving up and starts moving down. These are potential maxima or minima. They are stationary points in some sense, but not in the traditional sense, not in the dy by dx is 0 sense. They're stationary points in the sense that as something moves, it reaches its extreme in the x direction or in the y direction. Let's look at the picture to get a clearer sense of what's happening. In the y direction, it reaches its extreme right down at the bottom, somewhere around here. That's the lowest it ever gets in the y direction. In the x direction, that extreme happens around here. And if we look at the t values we get, -2, -1, 0, 1, 2, you can see that the two little green points correspond to -0.5 and 0.5. But then we look at the values of y dash and x dash, in other words dy by dt and dx by dt at each point, and you can see that we've got a sense of which way the thing is moving. It's moving down at a rate of 3 units per second, and it's moving left at a rate of 5 units per second, and then a second later it's moving down at a slower rate, only 1 unit per second. It's moving left at a slower rate, only 3 units per second, and as time goes by these things change. Now it's moving up but still left, and this one corresponds to t equals 0. The next one, corresponding to t equals 1, it's moving up even faster. It's now moving to the right as well. And then finally y dash is 5, so it's moving up at a rate of 5 units per second. It's moving right at a rate of 3 units per second. But if you look closely, you might notice, if we know the rate at which y is changing and simultaneously the rate at which x is changing, we can cut t out of the equation and get the rate at which y changes with respect to x. So that's what's happening here using chain rule. We do dy by dx is dy by dt multiplied by dt by dx. Some people write it as divided by dx by dt, which you can do, but you'll end up flipping it over to do the multiplication anyway. So we get an expression here which involves t. We can put different values of t in and we will get exactly what we'd expect, the gradient of the graph. Look at this first point at t equals -2. Y dash is -3, x dash is -5, dy by dx 3/5. The gradient's a third down here. The gradient is -1 here. It becomes 3 there and trails off a bit more to 5/3 over there. You can see the gradient at any given point. It's even undefined at certain moments, and if you tried calculating dy by dx at, for instance, when t equals 1/2, we'd have a problem because dx by dt is 0 when t equals 1/2, so you'd be dividing by 0. You can see that from the denominator of the dy by dx expression. The stationary points in the more traditional sense, they happen when the curve is horizontal. In other words, when dy by dx is 0. And you can find those values by substituting dy by dx equals 0. Notice we've got a fraction. If the fraction is 0, it means the numerator must be 0. So we get t equals -1/2. Sub those back in to get the x and y coordinates. So that's going to be this point down here. And if we want to know where the curve is vertical, which is not quite the same as a stationary point, but in a sense it kind of is. It's like a minimum from the perspective of going left and right. You can get that by looking at dx by dy equals 0. In other words, flip your dy by dx over and see what happens when that's 0. It's equivalent to when dy by dx is undefined. It's when the denominator is 0. And that gives this point. Here's another example. This one involves a bit of trigonometry, so if you've not yet looked at sine and cos and how they differentiate, which depending on the order in which you watch the videos you may not have done, you can make use of the fact that sine differentiates to cos, and a proper proof of this you will absolutely need at some point, but for now we'll be fine with these. We'll take them as read. Cos differentiates to negative sine. We can use that to do a very similar process here to what we did on the last page. So the equation of the normal at t equals pi by 6. We would take the x and the y and we differentiate them each with respect to t. dx by dt, the 2 disappears, sine becomes cos. dy by dt. The 3 disappears. Negative 4 cos t becomes negative 4 times negative sine t, so just 4 sine t. Then we combine them. Dy by dx is dy by dt multiplied by dt by dx. We get that delightful cancelling out of the dt term on the bottom and the top of that little multiplied fraction term. And of course sine over cos is tan, so we can just write it as 4 tan t. We've now got an expression for dy by dx. We can use it to find things like the equation of a normal. We'd substitute in the t value to get dy by dx, and we take the negative reciprocal to find the gradient of the normal. We could also find the x and y coordinates by substituting the same t value in to x and to y. And remember, unless it specifies that you should round something, you should always stick with the exact values. They want the equation, not some equation of a line very close to this, but the equation, the exact values. And now we just use y minus y1 equals m brackets x minus x1. And there's no need to try simplifying. It looks pretty messy if you try writing it any other way, so you might as well leave it like this. The next bit, the equation of the tangent when t equals, that's supposed to say pi by 2. So I'm going to change that in place. There's a problem here, kind of. We're going to see what happens. When t equals pi by 2, tan pi by 2 is undefined. The curve doesn't work, or does it? Well, the gradient is undefined, but that's not necessarily a problem. If dy by dx doesn't exist, that doesn't necessarily mean that dx by dy doesn't exist. We can flip it over, get a quarter of cot t, that's just 1 over 4 tan t if you think of it like that. But if instead you think of it as cos over sine, rather than sine over cos, it's perfectly well defined. We can get a value, we can get a 0. That means that what we're looking at is a perfectly vertical line, because although the rate of change of the y value compared to the x value might be infinite, the rate of change of x compared to y is 0. So the tangent is just a vertical line, and that makes it even easier in a way. We need the x coordinate to know what the vertical line is going to be, but as soon as you know that, we've got our vertical line, x equals 3.